The purpose of this video is to show you how to solve radical equations. I wanted you to get the notes at home so we could focus on some more complicated examples in class. So solving radical equations basically involves isolating the radical, raising both sides to an appropriate power, solving for the variable, and then checking for extraneous solutions. So I'm going to walk you through two examples here. The first example is 5 minus 3 times the cube root of 2x plus 1 equals 17. So the first thing we're going to do is isolate the radical. So we're going to undo everything that's being done to the outside of the radical. So there's a real temptation to put that 5 and that 3 together. Don't do that because the 3 is attached to the radical. So we're going to undo, reverse PEMDAS, the addition first. We're going to divide both sides by negative 3. All right, now the radical is now by itself. So now we want to raise both sides to an appropriate power. Now, because this is a cube root, the thing you'd want to undo that is to cube both sides. If it had been a square root, you square both sides. If it had been fourth root, you've raised both sides to the fourth power. So when you cube a cube root, those are inverses of each other. They cancel each other out. And when you cube, I wrote a 2 over there, negative 4, you get negative 64. So now I'm going to solve for the variable. So I subtract 1 from both sides. So that would give me 2x equals negative 65. And so x would be negative 65 over 2, which is negative 32.5. Don't matter if you leave a fraction or decimal. So now I need to check for extraneous solutions. Now, I'll tell you that extraneous solutions are far more common when you have indexes of radicals that are even rather than odd, but it's good to go ahead and get into the practice of checking. So if I plug negative 32.5 in for x into the original, 2 times that would be negative 65, plus 1 would be negative 64. Cube root of negative 64 would be negative 4, times negative 3 would be 12, and then 5 plus 12 is 17, so that's right. Now, we're going to do this with a slightly more complicated example now. So we're going to isolate the radical on this. So even though there's a variable on the other side of the equation, we want to get the radical by itself. So I'm going to subtract 2 from both sides. And the reason you want to get the radical by itself is for this next step. When you raise both sides to the appropriate power, which in this case would be a 2, squaring the radical is nice and simple. If the radical were not by itself, it wouldn't be so simple. It would still be possible, it just wouldn't be so simple. So that would be x plus 4. When I square x minus 2, that's a quantity with a subtraction in it, so I'd have to multiply x minus 2 by itself. Just keep in mind, x minus 2 squared is not x squared minus 4. It's x squared minus 4x plus 4, because that's what I would get when I FOILed out x minus 2 times x minus 2. So this is a quadratic equation, so I'm going to get everything on the same side by subtracting x and subtracting 4. And that would leave me with that. So this actually factors, it has a common factor of x, so I'm going to pull out the x, and that would give me x minus 5. And then I can use the zero product principle to get these two answers, x equals 0 and x equals 5. Now, when you go to check for extraneous solutions, if I check 0, if I plug that into the original equation, I would get, I'll actually write it out this time, 2 plus the square root of 0 plus 4 equals 0. So that would be 2 plus 2 is 0, and 4 is clearly not 0, so that is not an answer. When I check 5, I would get 2 plus the square root of 5 plus 4 equals 5. That would be 2 plus 3 equals 5, and that is true, so that is a solution. By the way, the extraneous values often arise when you square both sides or raise to the fourth, both sides to the fourth, because when you raise something to an even power, you obliterate whether the original thing was positive or negative, because the result always comes out positive, right? That's why this sometimes produces extraneous solutions in your answer when you have to check it. That's also why it doesn't happen with odd roots, because when you raise a positive number to an odd root, it comes out positive, and a negative number to an odd root comes out negative, so you don't get that extraneous solution produced. So we're going to talk about more complicated examples than these in class, but it's good for you to go ahead and have the structure of this down before we do.